Hello, I'm Bo Ewald. I'm the president of D-Wave International, and I help the company focus on customers and applications and software tools. I kind of grew up and grew old with high-performance computing. I've been at Los Alamos. I used to run computing there. Was at Cray Research, where I was the president, Silicon Graphics, where I was the CEO, and several other companies. So I've been in high-performance computing for a long, long time, and I've been fortunate to be able to work on quantum computing for the last 3 years. I think it is the most interesting and disruptive thing that I've seen in computing in a long, long time, maybe in my entire career. So basically what we have with D-Wave Systems are the first of the commercially available quantum computers. Our machines have been, I'll talk a little bit about the customers in a second, but our machines have been around for 4 or 5 years now, and machines are really suited for optimization problems, probably machine learning, and then thirdly, Monte Carlo or sampling sorts of problems. Without going into all of the quantum physics, the way our machine works, or a way to think about it, is that if you had, I'll start with 3 dimensions, but if you had a problem that you could map into 3 dimensions, mountains and valleys, what our machine does about 10,000 times a second is to find the lowest valley or valleys in that energy landscape, probably. It's probabilistic, so it's not guaranteed to find the lowest valley or valleys, but it probably does. So what it's really doing is searching through an n-dimensional energy landscape, looking for the lowest energy solution. But a way to think about it is energy landscape, mountains, valleys, probably finding the lowest valley. And if, depending on what the problem looks like, if the problem is like a piece of sandpaper, so flat with a lot of little mountains, you'll get quite a wide distribution of answers. But if the problem is like the Alps, or more so, where they're very steep and narrow mountains with valleys in between, and someplace there's one very low valley, then the machine will probably, most of the answers will end up being in that very low valley. And it will use quantum techniques to be able to find that low valley. So it is probabilistic. People don't typically run a problem one time to get the answer, but rather you run it 100 times or 1,000 times and get a distribution of answers. And depending on, again, what the problem is like, if it's these very steep mountains and one low valley, most of the answers will be in that low valley. So Google, who is our second customer, in fact, announced last December that they had learned about our machine and our 1,000 qubit machine and created a benchmark problem that has very steep, narrow mountains and a low valley. And in fact, when they ran that problem on our machine, it turned out to be 100 million times faster than on a traditional computer, which is a huge number. So now the challenge becomes finding problems that you can map onto this machine. We expect these machines to be used side by side with existing high-performance computers or data analytics engines, and that's what our 3 customers are doing today. So our first customer was Lockheed, who bought the first machine of 128 qubits about 4 or 5 years ago. They upgraded it to 500 qubits 2 or 3 years ago, and they're now running on a 1,000 qubit machine. Their primary application started as software verification and validation, and now they're looking at a broader set of optimization and machine learning problems. That machine is housed at the University of Southern California Information Sciences Institute, and so Lockheed users as well as USC, ISI, and their affiliates are using the machine. Second customer was Google, and the Google machine is located at NASA Ames in Mountain View, California, Silicon Valley. And again, Google has about half the machine, NASA Ames about the other half. NASA is, and their researchers through their affiliate USRA, are pursuing a broad set of research applications, and Google is more focused on machine learning. Our third customer came to be Los Alamos National Laboratory, one of the Department of Energy labs in the U.S. They purchased a machine from us last fall and began running on it in our factory at the time. And that machine is just now being installed at Los Alamos. And they will, it'll be in the unclassified environment, and they have a whole range of potential applications that they're investigating on it, optimization problems, some machine learning, scheduling for high-performance computers, those sorts of things. So the characteristics of those customers and ones that we see in the future are that, in fact, our machines will not replace high-performance computers. Our machines will sit side by side with high-performance computers or data analytics engines and will help them get better answers, is what we expect. The last thing I think for us to think about is the big European initiative in quantum computing, which we think is great. It's terrific, €1 billion or more going into the program. I think I would think about that program in a couple of ways. Number one, program will clearly help advance the state of things quantum, whether they be quantum communications, quantum devices, or quantum computing. But beyond that, in the long term, the most important contributions from quantum computing, I think, will not be the hardware devices themselves, but will be the software that comes from it. So our hope is, and I think people within the quantum computing community hope that a good share of that money will go to looking at algorithms and applications for quantum computing, not just the devices. In the long term, if you look at the computing industry, the biggest impact the computing industry, today's traditional computing industry, has had probably doesn't come from the hardware. It certainly started with the hardware as accelerators, but over the long term, it's been software. Software to design safer automobiles, find more petroleum, alternative energy sources, problems of national defense. Those are all software problems, and I think that's where in addition to the great research on the hardware side of quantum computing, I think the big frontier is in software for quantum computers, and that means algorithms, better software tools, the environment for it. So we're really right at the start of quantum computing, the era of quantum computing. I believe that with D-Wave, we have the opportunity to have a larger impact on the future of computing than we did with Cray Research or Silicon Graphics or some of the other great companies that I've had the opportunity to work with. So it's really exciting. It's early days, and we're looking for more smart people to help us figure out how best to do it.